In the last video, we talked about potential and kinetic energy, and I want to focus specifically on kinetic energy at this moment when we talk about temperature. So temperature is, the symbol for temperature is a capital T, but the units we use to measure it are degrees Celsius. And there's often a lot of misconceptions about what temperature is, but temperature measures the average amount of kinetic energy in the atoms. Okay, so temperature will measure if the atoms are moving very quickly or if they're moving slowly. And we can really only detect changes in that temperature. And so the kinetic energy comes in the form of heat. So heat is not really, it's not really measuring anything. Heat uses the symbol Q, lowercase q, which is a little annoying. You would hope that it was an H, but that is used for Planck's constant in when we talk about light. So heat with a lowercase letter q is the energy that is transferring. So heat is being transferred, and it's from one object to another. And what's important is it's because of a temperature difference. Okay, so if there is no difference in temperature, then there is no heat that is being moved back and forth. Heat is a type of energy. It's our thermal kinetic energy. And we can only detect changes in the heat or changes in the energy. So as it's moving in one object and out of another object. And so heat is going to flow from a hot object to a less hot object. And you might ask, why don't I use the word cold? Well, there is no such thing as cold. The reason why is because the word cold just means a lack of heat. So if you say, I'm really, really cold, what you mean to say is that you actually don't have a lot of heat in your body. You're releasing heat and therefore you feel cold. Cold is a word we made up to talk about how we feel, but there's no such thing as cold energy. And so when we measure these temperature differences, it's important to note where the heat energy is coming from and where it's going to, because energy is conserved. It will always have both a original location and a destination. And so we use the phrases system and surroundings to describe that. So the universe, everything in the entire universe is made up of our system and our surroundings. And the system is used to describe what you are studying or looking at. And basically whatever you're paying attention to. And so in a different scenario, two different things could be, it could be a system one time, but the surroundings the next time. And the surroundings is literally everything else. So if I am doing a science experiment and it's happening in the beaker and all I care about is this reaction, then what's inside the beaker is my system, and the beaker plus everything else is my surroundings. And as we talk about the way heat moves in and out of objects, we will use the phrases endo and exothermic. When we talk about endo and exothermic reactions, we really need to define what that means. So what we're going to do is we're going to split our note sheet in half. Well, that's kind of in half. Let's do that a little bit better. We're going to split endo and exothermic in half and define them. So endothermic, endo sounds like N, and so that is when energy or heat moves into the system. Another way of saying moves into would be is absorbed by the system, whereas an exothermic process is when energy moves out of the system. So energy moves out of the system. And another way of saying moved out, the opposite of absorbing, would be releasing. For endo and exothermic, let's pretend that our system is this box that I'm drawing. If our system is endothermic, that means heat is going into the system. And so that means that our system here, the system, our box, is going to start to feel hotter. Okay, but that means the surroundings, which are literally everything in the entire universe except for that box, especially the immediate surrounding, so the air right around the box, will start to feel cooler. They're going to feel the opposite. So if that box feels really warm, then anything that's right around that box will most likely feel colder than it was. Now, if the box, our system, is exothermic, that means heat is going to come out of the box. And so that means our system inside the box is going to feel cooler, and the system outside, or excuse me, the surroundings are going to be absorbing that heat that's being released, and so they will feel warmer. An example of this is when ice is melting in lemonade. So if the ice is your system, the ice is going to absorb heat, and so it's an endothermic process. And the lemonade is releasing the heat. So it's absorbing the heat that is released by the lemonade. And so the key thing about this is that it is confirming the law of conservation of energy. Energy is neither created nor destroyed. The energy to melt the ice, the heat, is coming from the lemonade. And so an example of an exothermic process where the system is going to feel cooler and the surroundings around them are going to feel warmer is a runner who is done with a race. Okay, if they have just run a race, their bodies are going to start releasing heat in order for their bodies to cool down because they have all this energy that they've just been using to run this race. And so you might be able to see an athlete, if it's cold outside, you'll be able to see steam rising from their bodies. And that is because the heat that they're releasing is being absorbed by the sweat on their bodies, and it's literally enough to turn into a vapor. And so there's the runner is releasing heat, the sweat on their bodies is absorbing it, and it's turning into a vapor. Now, when these are physical processes that we're describing, but a chemical reaction can also be classified as being either endo or exothermic. So for an endothermic reaction, you're going to have your reactants plus energy make your products. And so this means heat is required in the reaction. So our reactants could be A plus B plus, 40 joules of energy produces C. Okay, that could be our reaction. And so the key thing, though, is knowing that energy is a reactant. For an exothermic reaction, you're going to have your reactants produce heat. Remember, heat is being released, it's being made. So your products are going to form and your energy will be on the right side of your arrow. And so the reverse of our endothermic reaction would be true. If you have product C, it could decompose or break apart into A plus B, and that would release a lot of energy. So it might release that 40 joules. One thing to note is that your energy, your change in energy is also caused by the breaking and forming of bonds. So you can see this in graph form, where if you have the time of your reaction on your x-axis and you have energy on your y-axis, energy measured in joules, you'll see that your reactants for an endothermic reaction start out lower than your products do. So these are our reactants, and this is the energy level of our products. And what occurs is your reactants are going to absorb energy, and eventually they'll reach the point where the reaction is starting to occur at the very top of this hill, at the peak amount of energy, and then energy will be released and your products will be formed. And so when energy is being absorbed as the line goes up, it can also be released. And so just because the endothermic reaction means energy is being absorbed doesn't mean that there's also a little bit of energy that is also released. But you can notice that as I go from reactants to products in general, our delta H, our change in enthalpy or change in Q, our delta H is equal to Q or heat, is positive. It is increasing in value. And if we look at our numbers, like if we were to give this actual numbers, let's say, and I'm making this up, if this was 100 joules and our reactants started out with their bond energies being around 20 joules, then our delta H would be 100 minus 20, which would give us 80 joules, and that's a positive 80. So 80 joules was overall absorbed by our reaction. And the reverse is true for exothermic. So if we draw this same graph, okay, where we have time on our x-axis and we have energy on our y-axis, the products, well, the reactants in a exothermic reaction are going to start off higher than our products. So here our reactants are starting off very high, our products are starting out low, and just like our endothermic graph, our exothermic graph will absorb a little bit of energy, but not nearly as much as it releases. And so you can see that this small increase is when energy is absorbed. So if you think about lighting a match, you have to hit the match against the matchbook in such a way that it will light. It doesn't spontaneously burst into flames. Okay, you have to put a little bit of energy in, but the energy that is released by a match is much greater than the amount that you put in. And so the delta H here, okay, the Q, if you draw an arrow from reactants to products, it's pointing down. So our delta H, which is equal to Q, is negative. And again, if we assign random numbers, again, if this is 20 joules, our products have bond energies of 20 joules, whereas our reactants have bond energies of 100 joules, then our delta H would be equal to 20 minus 100, which would give us negative 80 joules as our delta H. And so endo and exothermic is so crucial to this unit of how energy moves in and out, what positive and negative Q values mean about energy being absorbed and released. This is the crucial component of our unit.